everybody, here and there. So I'm Joël Falcou. I will be entertaining you this morning. I hope so, actually. So yes, I'm going to speak about Eve, which is a C++ library for simplifying or actually helping people write vectorized code so they don't have to deal with most of the inane stuff you probably saw last week. A few logistic points. So everybody probably online can also benefit from that. If you really want to follow the slide at your own pace and whatnot, you can go to this page, events.coderecons.com/eve, where you will find like the slide deck actually, so you can play with it if you want. This page will be up after the school, so you can get back to the slide, all the info about the library. This is actually linked to the corresponding part, and I will put up the examples we are going to show this morning, also for later consumption. So you can go there if you want to follow along. In the great tradition of I prepared everything except what I forgot to prepare, for people using the Docker image from Eve, there is a V2 that was uploaded yesterday that fixed some missing parts and put the library in the Docker to the last version. So if you are somewhere else and you want to update your Docker, that's the moment to do it. The name of the Docker is on the Discord in the C++ course channel and the organizer one. So you can fetch it there while I'm trying to make an introduction. Yeah, we are going to speak about Eve, among other things. Let's get a refresher because it was already last week. So we are going to speak about vectorizing. Okay. So the question is, why do we want to do that? What's the complex part? Okay, and why tools are needed after some level of complexity? So for those that weren't there last week, you probably remember something like that. Yeah. If you want to, oh, sorry. Yeah. If you have a regular CPU, you have one data in, one instruction, and somehow at some point you're supposed to get one result. Okay. It's a bit more complicated than that because like superscalar processor, pipelines, whatever. Micro instruction and out of order stuff, but that's a classical thing we are supposed to run. Obviously, this doesn't go as far as we want, and a long time ago, like in the late 20th century, some clever people came up with another idea, which was, what about we have large registers, okay? So we can put more data in a single register, okay? And then we have a special arithmetic unit that just consumes this special register and consumes them to give us some special results. The idea is that the clock at which those large registers are processed is the same than the other one. So instead of processing one data per cycle, we can process 2, 4, 8, 16, or whatever. And thus we expect, if everything goes right, that we are going to get a speed up of about something, proportional to the width of those registers. So that's cool, okay? That's a great idea. And the question is, how do we actually access those things? So yeah, there is different way to do that. There is a different flavor of CD. Obviously, in the grand scheme of things, people like to have their own version of those tools. So everyone and his mother has these special architectures, okay? x86 has, I don't know how many now, we are going to see that a bit later, but there is 5 or 6, what?
35, I counted.
35, thank you. Yeah. I was at 27, but they probably had some AVX512 I don't know about. Yeah.
Special purpose one for crypto.
Obviously. So there is 5 128 bits versions. There is 2.5 to 56, and there is I don't know, far too many 512 bits version. We are going to deep into that a bit later. But as we see, there is quite a bunch of technologies. I'm speaking in terms of bits there. What do I mean by 128 bits? That means that the registers on those architectures provide SIMD at this size. So registers are 128 bits. So if you are, I mean, it's 9 o'clock, so I know it's a bit complicated. But you work with double. That means that you have 2 double in your register, 4 floats, 8 shorts, 16 char, or other 8 bits data. And we see that rising the size of the register basically just gives us more latent parallelism. Okay, so AVX and its 256 bits means that we have 4 doubles per register. And LX512 up the NT up to 8 double per register. How much is that? Okay, wait. 1632, 64 chars per register. Okay, well, that's just x86. Okay, there's basically the same idea between all those variants, except obviously the API are vastly different depending on the version. But that's only if we look at x86. I kinda heard, that other architecture exists. So if we look at other people, we see that ARM has a bunch of them. The most common is probably Neon and its 64 bits version, which is a different name, SMD or RR64, whatever. If you have a phone with an ARM inside, you're probably running this. And there is the old SVE, SV2 family. What we are going to speak about that a bit later because, yeah, they don't behave like the other one, even if they are similar instruction sets. And they go up to 124 bits, so they say. In the wild, the biggest we saw was 512. So let's say that. And then there are other things. You have the great ancestor, PowerPC, as senior instruction set since 1997 with, oh, come on, with Altivec, which has been updated but not upgraded in terms of which registers. There was some 256 bits attempt with the Blue Gene Q, QPX things, which was a good idea because it was 256 bits, which was a bad idea because it only works on double. And nowadays, so we have RISC-V, obviously, which is probably the hottest one right now, that has some variant of a SVE-like SIMD register. WASM has some support for SIMD, so basically, it's everywhere. So that's the good news. I mean, if you pick an architecture, you probably have something that supports SIMD somehow. Okay? The problem is, if your job is actually to write efficient code using SIMD, but you don't really know which architecture you target, it starts to be a mess. And to be frank, it's a mess even if, well, you only care about that. What's the correct basic target for x86 nowadays? Should I stay, conservative and target stuff like SSE2 or SSE4? But that's architectures that are decades old already. Is IVX2 a safe bet, or should I go all in and do IVX512? Spoiler, don't. And if you need to cross across architectures, I mean, yeah, welcome in air. So why is it why may be an issue? Maybe, I mean, if you do science, which probably most of you are doing somehow, most of the time you don't really have this problem because you work on a given machine or given supercomputer or whatnot. It's not going to change soon, okay? But sometimes you have to write components, libraries, or applications that you can use differently. And if you send out a binary library somewhere or component somewhere, you have to know what kind of stuff you are targeting. So nowadays, let's be frank, SSE 4.2 is the very, very minimum. AVH2 is probably now a decent default. AVH2 is like, what, 2010, something like that? I will check. So it should be everywhere. So, yeah. But it's a mess because as soon as you want to port something, although, I mean, you have your simulation code on your x86 and now your new supercomputer is all ARM and whatnot. Well, if you didn't do your homework, you have to write everything again. But how do I access that? I mean, okay, there is a plenty of things. Well, let's auto-vectorize. Now, I'm not going to repeat what you probably heard last week, but auto-vectorization exists. When it works, you take the win and you go doing something else. But most of the time, it won't work, or it will work with additional changes that may or may not be portable across compiler or across architecture. So you are at the mercy of whatever the auto-vectorizer wants to do. But again, if it works for your exact use case, you're done. Don't try to do anything else. We have to be pragmatic. Okay? Until the next time the auto-vectorizer broke, okay, and you have to change it anyway. You can maybe use stuff like OpenMP Pragma, which are slightly better. Probably 80% of the time what they do is they force the auto-vectorizer to auto-vectorize, but there is for that. There is some special compiler. ISPC is one thing that comes to mind. There is some standard or pseudo-standard support for that. I should have updated this slide now. But you have the wonderful STD execution unsec policy, which is supposed to be put on an algorithm in standard C++, and bam, it's vectorized. Or so I heard. You have HPH, which contains a version of that, implemented in a different way. And now, as it has been voted in C++ 26 last week, STD SIMD is a thing, okay? Maybe you need just a very specialized tools, like you have one very specific task that can be outsourced to a already manually vectorized library, stuff like ALID if you do image processing, or SIMD-JSON if you have the absolute banger of a task to read large JSON file. Or if you have a lot of free time or a lot of interns, depending on where you are on the food scale of the academic things, you can write it by hand. Sounds a good idea. I mean, where are they? Yeah, I mean, you have wonderful documentation, you know, with all the things you can do in SIMD. Okay, I'm not going back because I will probably get a tennis elbow, but you get the idea. So you probably can do something with that. Yes, you can, probably. That's the key word. I mean, it's full of complex stuff, okay? And if you don't really know what you are doing, it's a bit complicated to navigate that. But now, let's say you want to do this because your algorithm doesn't fit what the auto-vectorizer can do. You don't have any pre-made library for doing it, and the standard or pseudo-standard solution doesn't live up to the hype. Yeah, let's do that. Let's write some SIMD by hand. Yeah, let's just do something easy. Let's write 8 times b plus c with integrals. Okay? Yeah, we can conjure some, dark magic rituals to get that working. Okay, foraging in the doc. Okay. The most intriguing part is this function. Why isn't this just mul? What is it mul low? Because good luck, there is no multiplication for 32-bit integer in SSE4. So you have to take the one that takes the lower part of it, because the only stuff you have is 32 to 64 bits multiplication. And it's even funnier if you have to write an AltiVec version, because you only have FMA on float, so you have to convert your integer in float and back with all the problems that entails. And that's just multiplication. If you look at all the intrinsic supports everywhere for any kind of architectures, you will find two things. Either you have the function you want, but not for the type you need, or you have the type support you want, but not the function you need. Or sometimes you have the function, but half of it, because you know it should be too easy if not. So it's a game of Lego. So I pondered about redoing this joke this year, because I already did this joke last year, but I remember that this year was in English, so it counts as a new joke. Working with bare hands SIMD code is basically you are handed a basic Lego set, you know, those big box you can buy for 30 euros, and you have like 2,000 pieces in red, yellow, blue, pink, white, and you're tasked to make an accurate model of the Death Star, which is all gray and black, you know. So you have to be creative, okay? So let's do that, you know. So there is a lot of, how to say that? How to say that this way? There is a lot of oral tradition in the the circle of people that write simply code by hand, which has now turned into written tradition because Stack Overflow is full of interesting questions. But there is a lot of tricks. A lot. And by a lot, I mean a huge lot. Okay. We are in 2025, and someone found a better way to compute the conversion from 8-bit char to floating point value last month. Okay, that's this kind of, oh, we didn't think about this, which is actually, I mean, let's go back to that, which is not a big surprise if you look at the complexity of the things, okay? Yeah. So either you know the tricks and your code is really efficient, or you don't know the trick and your code is meh, okay, but it works, okay? Or you don't have any idea how to turn your code into something that is vectorizable at all, until someone actually told you that, oh, you look at your problem the wrong way. If you look at it that way, it's obvious it's vectorizable. So one person that already has his mind, loaded with, I know how to do physics, I know how to do simulation, I do some math with strange letters and whatnot. You cannot ask all of those people to, on top of that, absorb, I don't know how many years of, oh, do you know these cool tricks of computing this fast on your machine? Okay, you cannot do that. So we need tools. That's the page. So that's what we try to do with Eve. So Eve, it's the last incarnation of a very old project that started in 2000. Oh God, 6, 5. Yes, that's it. It started in 2005 as a wrapper for ActiveX on PowerPC. It was back in the day where PowerPC was seen as a viable architecture that give you the time frame. And it evolved through many forms, different names, and we are now going back to the original name. And what we want to do is, first thing we wanted to do back in the day was to say, oh, we are going to write a library if we just vectorize everything. And turns out you cannot do that. I mean, it's too much of a task. It's too much of, how to say that, a wide field to cover. It's also something with moving goalposts sometimes, depending on the architecture, depending on the version of C++ you want to target. So we regrouped around this notion of we want to facilitate CMD programming by covering all the basics, giving wrappers to all the things that are complicated, but letting people be able to express how they want to compile their code, how they want to build their expressions, their algorithm, and whatnot. So that's basically how we wanted to have it. And obviously, like all those kind of projects, it just grew out of that. Mostly in terms of functions. Okay, I'm going to go over that a bit afterwards. And what we tried to do was to keep up every year or every so many years with whatever architectures were coming out. So the first target for Eve was PowerPC ActiveX, and then we covered the basic of x86, SSE2, SSE3, then we consumed all SSE as soon as they went. We moved on AVX when it came out. We moved on ARM in 2012 when Neon was started to be something that makes sense to use, and so on and so forth. Currently, we cover with quite good coverage, everything x86, everything ARM. Okay, maybe not all of SV2, but we are getting there. PowerPC also. We have tentative support for RISC-V. Which basically means that it compiles basic code on it, but it's not optimized yet. It's boost license, so yeah, we don't really care about what you do with it. For a while, it was dual license. We had a boost license and we have a postcard license. So if you use Eve and you live in a cool part of the world, send us a postcard and you get your license. Okay, wait, sorry. It's also a team effort. We are like, how many people now? 5 people, full-time, I would say, with a couple of transient contributors and interns and students that contributed. I mostly deal with the core library. Dennis is the very good guy that wrote us our algorithmic supports. Jean-Thierry Lapreste is the one doing the math with a capital M, you will see later. And Alexis is currently working as a PhD student, working on Float 16 and stuff like that. So we are on GitHub, okay? We even have a documentation, and if you have issues or you want to pester us about your algorithm or some function that doesn't work, you can find us on Discord, and we will be gladly answer your question. So yeah, so the GitHub is there, okay, classical things, okay. We have the documentation in which, well, you have a small tutorial if you want to have a look at that later, and we have our list of stuff we do. So we have some functions, okay, like all the basics you can find, like arithmetic functions, okay, logical, bitwise, some predicates, conversion operation. I know that Pierre, like this one, we have like EEE 574 operations. So if you want to vectorize a bit of sign, exponent, FRX, and all those funny things, you can, okay. Basically, you can consider that if it's somewhere in libc and libm, we probably have it. Probably means that we have it, but maybe not under the name you think it is, but we have it. We try to follow the naming scheme, but some make no sense, so we have our own. We have a bunch of constants also. Yeah, generic ones. Yeah, a bunch of them. Some math stuff. Okay. And then we have math functions. So, or everything, logarithm, exponential, trigo, inverse trigo, hyperbolic, and whatnot. Including, where is it? The wonderful cubic roots, obviously. And let's take this one, for example. So yeah, we got a bunch of information there. And usually you have a small sample there that whenever the internet is ready, should give you the output after a while. Yeah, there it is. So you can actually have a look at that. Every sample code, you can copy paste it or run it on the proper server to play around. So yeah, we have a bunch of stuff like that on the main API. There is also advanced math. So that's the part that I know it works. I saw the test, so it's okay. But that's more Jean-Thierry's thing. So we have vessels, combinatorials, special function. Yeah, some of them I don't even know what they do, but let's pretend. Yeah, so if you are into computing integrals to whatever place this is, yeah, you probably have it. Yeah, and you have stuff like trigamma function, you have a bunch of polynomials also, whatever. Yeah, it's a bunch, okay. Some of them are vectorized, and I think we are the only source of vectorized function like that. Most of the special functions are not that good in terms of efficiency. I'm not going to guarantee you that our Bessel function get a speed up of 4 on SSE in float, but they got some amount of speed up. And it's a cool way to not break, the flow of your vectorized code. I mean, it's not because you need a special function in the middle of the algorithm that you are going to lose the vectorization. And obviously, we have some SIMD-specific things. We are going to speak about that a bit later. And one of the most important are shuffles and reductions. We are going to have a look at that. And we have, as I said, some algorithm and views. Okay, so this part of the documentation is still a work in progress, but yeah, we have a bunch of ranges and conversion to ranges functions that let you build a bit more complicated subset of operation. Okay, so let me just put that. Pop. And let's go back there. But let's go back there. Right? Let's talk about tricks. Okay. Let's just have a look at what kind of thing we are speaking about. You may think that something simple, I don't know. Let's compare. Well, let's use some common sense. Okay, we are not going to have a look at AVX512 because it's like too many, but Yeah, you want to compare some integrals. So where are they? Can I do comparison on integrals? Well, no, I cannot. Oh, come on. Oh, where are you? Where are you? LT. Yeah. So we have that. So that's less than for 16-bit integers. Yeah, fine. Cool. Yeah, except one detail. It's signed. So what do I want? What should I do if I want to compare unsigned integers? Well, you cannot just put them there because it won't work. It will just reinterpret the bits as signed integers. So you have extra work to do. You have to take your unsigned, convert it to signed, shift it so you know everything is in the correct place, do the comparison, convert it back. And you start at this level. I mean, you don't even have a full-blown comparison system because it's not there. It's only partial. And it goes worse from there. Okay. So, how does it work? That's the question. Nope. The other button, sorry. Let's do some kind of, BAM example. We are at the point where we can safely write stuff like this. So that's basically a vectorized strlen, okay? And actually a portable vectorized strlen, because this code compiles everywhere, give us the correct code. Okay? In this case, it's rather simple because there is a vectorized strlen already in some libc, so we can actually compare to them. And we are basically accurate at most of the instructions. Strlen is not something you think as a vectorizable algorithm from the get-go because you are looking for a zero, but you don't know where it is. Okay, it's not like you are going to process. At some point, you are going to process something, and the zero is somewhere in your vector. And you need then to stop. You need to find a way where the zero was. So basically, that's what we do here. So the idea is basically taking the data, loading them somehow, computing how many bytes we should have a look at because we load something in a given way and there is some garbage at the beginning. And we are trying to find the zero in these things. If we don't find the zero, we are going to move up by the size of the register, load another piece of data, try to find if there is a zero there, up to the point we find it. And when we find it, we know that these things contain the position in the last vector where the zero is. We add it to where we are at the moment in terms of pointer in the memory. Okay, so we are there, we add the move, and we subtract the origin address. And so we have the position of the zero inside. So that's the simplest version. The actual correct version we have as a demonstration in the library examples. Do that and do some enrolling, because if you need to enroll that to get the correct performances. And on most architectures, we are basically on par with the actual vectorized strlen. Except instead of having a couple hundreds of assembly code, we have like what? Dozen lines, okay? And when you know what the function does by looking at the doc, it all makes sense. So, which also allow me to introduce a bunch of things. So we have an align PTR type, which is basically a pointer view to something that must be aligned in memory. Memory alignment is something you sometimes you want before processing your CIND data. Okay, you go faster loading aligned data. And we have a bunch of functions that can, from an address, give you the proper aligned version before or after. So we have a whole bunch of memory handling functions also at the common, at the lowest level. Okay. And we have this ignore thing, which we are going to speak about a bit later, but basically we can do masked operation. Okay. So we can decide which lane of the register is processed or not. And the rest is basically just advancing the pointer, loading data, doing this reduction. First true give you an optional, contains the index inside the register where you find something that is true. So we are trying to find the first place where this comparison is true. And everything just, work out. So let's have a look at the thing there. Yes, I moved too much? No, tell me. Oh, yes. I'm completely stupid. Yes, I will do that. Yeah, sorry for that. So wait a sec, because this thing is not. Yes, that's exactly not where I wanted to go, but fine. Okay, so let's do this. Let's have a look at. Yeah, I don't need the test actually. So the test is probably too much. I just need the function.
Joël,
Yes,
can you zoom a bit, please, for
that was I was going to ask.
for the elder of the
Yeah, for the
the Muppet Show?
come on. Yeah, so I'm going to zoom anyway. Yeah. So let's do this. 28. That's the best I can give you. Okay. I can make it do. I can do it there. Okay. Okay. Fine. Yeah. I was a bit. Okay. Okay. Why is that? Oh yes. So let's pretend to see. You see nothing. I forgot that we need to. We didn't update it somewhere. That's not what I want to do, Jude. Okay, so whatever. What I want to have as okay, compacts. Okay, fine. So I'm zooming this one too. Yeah, I didn't forget it. So this is Clang. Okay. What I'm looking at is somewhere I should have. Yeah, should have a loop. Okay. So yeah, we move, we compare, we get the mask, we test, and we jump around. GCC do something very similar, if I'm not mistaken. Yeah, where are you? Yeah. So we have this tight loop. So it's not unrolled. We should unroll it if you want to go fast, but give you the idea. And the cool thing is that I can actually move to AVX2 just by changing the compilation thing. And now we are using YMM things. Yeah, if we add the ARM compiler, we could actually do the same and we got ARM things. What if I go like, okay, Skylake, I want to or whatever. No, come on. Is it Skylake? I think it's Skylake. First one. Yeah. Yes. Okay. Where is my loop? Oh, come on. Oh, there it is. So again, we do exactly the same thing, and this time we go through the special ME 512 binary mask thing that we just want. So as soon as we unroll that, as I said, we are going to be on par with whatever. But the cool thing is that we are basically just generating exactly what we need. It looks like, if we look at that, I mean, we have some complex function there that load the things, and then we do a reduction, and we do a comparison, and then we get an optional out of that. Okay. Yet we just output code that makes sense in terms of number of intrinsics and number of operations. What's the deal? Well, the deal is that, and if you already did at home, we are paying this performance upfront at compile time. Okay. Most of the library do some intense template shenanigans to get to this level of performance. So it may sound like it compiles a bit slowly sometimes, but we are working on that. So we are able to go at this level of complexity. We also have, if you look in the example repository in the GitHub, you can see that we can go far in terms of complexity. So we are okay in terms of basic blocks. Okay. So now let's dive into the details. Okay. So the main component of Eve is the wide class. Okay. A wide of T is basically a register that contains value of type T in the proper amount with respect to whatever your architecture is supposed to use. So if you are on AVX2 machine and you have a wide of float or a wide of int, you are supposed to get 8 elements per register. And so the choice we made in terms of API is that the size of the registers is an optional parameter you can pass to while. And what we advise users to do is to just use while of t and let the code be written as in an architecture agnostic way. Okay. So you can construct while by filling it up with a constant. Okay, that's a trivial thing. Okay, you can fill it up with a generator formula. So you can initialize the while from a lambda. The lambda takes two parameters. The first one is the index of the lane you are currently filling up. The second one that you may or may not be using is the cardinal, the size of the while, okay, the number of elements. So in this case, what I do, I just build up 1 over the index of the lane. Okay. You can also fill up a while by loading it up from a piece of data in memory. Okay. So you can actually load. So I load some doubles starting from index 2 there. Yes. Or you can also, as I said, you can choose to fix the size of your while using this fixed parameter. So fix2 means that you want a while of two things, okay, two lengths, and you can specify them this way. Obviously, we have a bunch of guards for, if you ask for 4 elements and you fill it up with 7, you are going to be notified that you should read the documentation. This is necessary for some piece of algorithms, but usually you don't want to do that. But it's there, so you can use it if you want. And so if you print your whiles, you get whatever you expect, okay? And you can play around with that and see what's going on. So if we, again, go there, let's try to see what happens when we just, okay, oh, I need to, yes. Okay, thank you. What's the what? Oh, yeah, sorry. I don't have AVX 512. Yeah. So let's compile it like this. Yeah, so we are, oh, sorry. So we are compiling with no option on x86. So the base default is SSE2. So we have 4 elements for int and float, and we have 2 elements for the doubles that we saw there. Okay. One thing we can do is that, can I know which kind of architectures I'm currently compiling for? So we have this current API object that you can use for comparisons or for operation like that. So it will just tell us that we are compiling. Yeah, we are compiling for SSE2 at this time. And when you change the whatever the compilation flags, yeah. So now we have twice as many. Okay. And yeah, we got this. So we get ADX2, for example. Yeah, and we also support FMA extension. Or should we? Okay, fine. So sorry, my internet is acting up, I guess. Yeah, no, we don't want to. Okay, it doesn't want to compile. Oh, maybe I don't have FMA on this one. Okay. No, he's back. I thought we had FMA, so let's just find again. Yeah, well, we have FMA. So this is a small tool we have, so you can actually check out that we are not doing some silly things and whatnot. Well, that's the basic. There is another basic things that is provided, but usually you don't have to write it directly because it's automatically written. There is a question with vectorization about what's going on when I want to do a comparison. In scalar mode, if you compare two floats, well, you get a bool. Fine, okay, true, false. But the bool is like 8 bits. So if I have a wide of 4 floats, yeah, I don't really want to have a vector of 4 bools because it will be not using the YOL registers. So 99% of the assembly instruction sets have a special way to handle binaries, which is to have Boolean, sorry, to have Booleans represented into the same type as whatever you are comparing. So when you compare floats in a single register, you end up with a register of float, which has the funny effect that false is 0, that's fine, and true is none. Okay, it's true in Cindy is your bits of every register to 1. So you have 0 and none, which is not very, fine. For integers, it's 0 and -1 if it's unsigned, and so on and so forth. So you need an abstraction on top of that, unless you want to go crazy. And so what we have is that we have a type called logical, which is a logical value. And logical wraps anything and contains a Boolean of the proper type to represent a comparison on that. So you can have a logical of int, which is a single Boolean, actually. And you can have a logical of wide of int also, stuff like this. And for example, let's do what? Yeah, let's do a logical of float because it's not, it won't be funny. Okay, how many elements in Y are less than a quarter, for example? So you can have that. So you can compare lengthwise, wide with wide. And obviously what happened there is that if we have a look at them, okay, normally they should have the correct result, obviously, but yeah, I mean they act as Boolean. Okay. They internally store the data the correct way, obviously, because it won't work either. But they are stored as something that for us, the user behave like a Boolean. Okay. But the question is, I know what to do with a Boolean in Scala. I can do if else, I can do stuff like that, but I can surely not do that in SIMD because if else is a control structure. And so it's a bit like when you do GPU, you cause some divergence. So how do you do that? Well, a bit like GPU. Well, I will be frank. GPU just do like we do, but you can actually do lane-wise comparisons. So you can write stuff like that. I mean, what's the shape of my YE? Okay. You know what? Let's go back to 4. So we can have the big display and it fits into the screen. So what you can do is doing something like that. What I want is I want to have some value M. And what I want to have is basically if Y is less than a quarter, I want some value. I don't know, like the square of Y, and if not, I want some other one. So I need to do an if else. Well, that's cool because we have an if else function. So the if else function weighs 3 parameters: the logical condition, the true value, and the false value. So let's reuse. Oh, let's do that instead. So am I bigger than a quarter? If yes, I want Y squared, and if not, I don't know. Let's go to the square root of Y, for example. So if else is actually a function. It cannot be anything else. And again, if you have the habit, if you have the experience with whatever happened on some other stuff like GPU, it's a bit like a divergence. We need to compute both branches first, and then we select based on the binary logical value. So let's have a look at M there. Yeah, a quarter is about too big because obviously the thing is too small. So let's say a half. Okay. So yeah, whatever. So 1 square is that. Okay. Sorry, square of root of 1 is 1. Square root of half is 1 over square root of 2. And then we square away the rest. Yeah. Okay. Is it? Yeah. So if else, we can actually vectorize selection. Sometimes what you want to do is something like this actually. You want to do that, let's say. Something happens and then you modify your value or you let it as it is. Okay. And sometimes what you are going to do let's do it this way. It's just that you want to do that. So that's a conditional operation. So I want to do a plus if and only if something's true. And if not, I don't want to touch to the original value. Some SIMD instruction sets have special operations for these things. It's what we call a masked operation. Okay? And so a masked operation will just touch the lane of the registers at the condition, where the condition is true. This is useful for a variety of tasks, including the fact that, as we saw in the strlen example, sometimes you know that you loaded garbage from memory, or you know that you computed something and you have a bunch of nans somewhere and you don't want to touch them, so you want to filter them out. Okay? So if you were into a scalar way of thinking, you would just do a loop and you would do some if inside, and you just keep over the baked data. But we can do that. So we have to process everything. And you can write it this way. You could use if else if you want, but if you do this, if else only know about doing an if else. It doesn't know about the fact that you are doing some operation inside it that maybe is already masked. So what we have also is that you can actually apply mask operation. So we played around with square root at some point. Okay, so we know we have functions. So let's say what we want to do is we only want to take the or we want to take the square of y only if something is greater than something. So what you can do is let's take the square, okay, of y, but only if y is greater than 0.5. Okay? So we have this notation with the brackets on top of the function. So we do yes. The other way around. Should have put better data in this way, but whatever. Let's see. Yeah, better. Okay, wait. Yes, yeah, okay, that's it. Okay, fine. I was confused for a bit. So yeah, what does this mean? That means that we are applying the function, there it's square, only in the lane where whatever the condition in the brackets is true. And if not, we just let the whole data in. So for one parameter function, it's rather trivial. For multiple parameters, if you don't apply the function, you get the first value. You get the value of the first parameter of the function. So if we did that, for example, if we add y to, I don't know, like 7.25 or whatever, the place where we are not touching, okay, we got the value of y, which is not the same as doing this. Okay? So if we do it the other way, we get the 7.25. Also, we remark that we can do broadcasting there. I mean, you can mix wide and scalar constant without having to think about it. So on some architectures, this is basically translated to an if else because you don't have any other option. But on the latest architectures like some ARM, some SVE, some IVE512, you get actually an actual special intrinsics for that. So let's see if we can have a look at that. Oh yeah, except it's full of prints, so it will be bad. Let's do that. Let's write a small function out there. So you can obviously pass, wide as function parameter. We are going to speak about that a bit later again, but that's the obvious. So let's put that in the function so we can have a look at what the assembly code is generated. Okay, so this is SSE2. So in SSE2, we don't have much. We don't even have an if-else intrinsic. But what we can do is that we can compute the comparison, okay? And then what we do, we use the mask, the binary mask, to do AND and OR over the true data and the false data, and then we squeeze them together. That's basically what happens there. So it's a bit of a mouthful, okay? But that's the best we can do in SSE2. But hopefully for us, starting SSE3 or something, so let's say SSE4, we actually have, yes, I saw you. Yeah, we have a blend function that just do this and not or in a single cycle, okay? So we get the comparison, etc. So let's do something else. Let's clarify this assembly because there is a lot going on. Let's say we pass the mask as a parameter. So we can pass a logical of y there, m, like for mask. So now we have like one thing less to compute. The mask just come in. Yeah, and so the first part with the show PS is converting the scalar into a y. Then we do the add because we have to, and then we blend the result with the other one. Okay, so that's better. But what's actually better is what happened on higher architectures. What do AVX2 does? Yeah, they have a broadcast function. Sounds better, okay, instead of having to load and broadcast and to shuffle and whatnot. And if we go back to our good friend AVX Skylake 512, yeah, we broadcast and we have this nice mask add. Okay. There is no blend because there is no need to blend because AVX 512 have a mask add operation. Okay. So there is one more thing we can do is what if I want to do this conditionally, but what I want to do, okay, it's, let's go back to this, for example. What I want to do is that if I'm not doing the computation, it's not that I want y to be put back. I want another value altogether. I have an alternative to my if. Okay. So what we have there is that we have a mask. Okay? That's not enough. We want a mask and an alternative, right? So what we can do is we can do, well, if m is true, then I want to apply my function, else, I don't know, I want to put some other value, right? I want to do something like this. So let me just, so basically we are saying, okay, I want you to mask, and if the mask doesn't work, I want you to use that instead of the first one, okay? And yeah, that's basically what we do. So again, we have the mask add that do the whole thing as a single instruction. Okay. ARM also have mask operation. And if not, I mean, if I'm not using this, if I go back to whatever I add, I do the correct thing anyway. So there is some benefit to write that instead of writing if-else. Sometimes you want to write if-else because it's a complicated if-else. You do some comparison and you do some tricky things with different variables and whatnot. But if you can express your operation as a mask operation, there is a, let's say, a future-proof benefit so that whenever you move to another architecture, we are able to generate the correct code. The syntax is what it is, mostly because I cannot reuse if and else because they are keywords, but that's the gist of it. But there is more than just having logicals like that with a random mask. There is some special mask that is useful sometimes to use, that we call the relative mask. Sometimes you will end up with operations that when you translate into vectorized code, you want to do something everywhere except for the first lane of the register. Or everywhere except for the one in the middle or something. Or you want to ignore some lanes based on their index. Okay. So what you can do, let's send this good old logical down the drain. Well, I can do add. Yeah. Let's just. I can do add. Let's do it this way directly. I want to do add, but I want to ignore the first one. Okay. So we can ignore first the thing, okay, between y and y, for example. Let's go back to running the code. Yep. Yeah, so yeah. I do y plus y, but oh yeah, I ignore the first one, which is a 1. Okay. Oh no, that's good. That's okay. So I didn't touch there. Sorry. I didn't touch the first one, and then I do the operation on the other one. And obviously, you have the whole family, ignore first, ignore last, keep first, keep last, and so on like that. And so you can pass values there to express the way that you want to ignore some amount of that. So I put a constant there, but as we see in the strlen sample, we can actually pass an arbitrary value. Okay. So let's have a look at the generated code, however. What if I ignore the first one there? Okay, I can do that. What kind of code do we have? Well, this is SSE4, so I don't expect much. Yeah. So what we do is we have to compare the index with whatever value we need before blending. Okay. LVH2 is no better, I guess. Well, we are going to save the broadcast, but that's pretty much all. Okay. And again, as we move up into the most modern architectures, SkyMake, not Skylake. Yeah, it's even better there. Remember that I told you that mask on 99% of the senior instruction set is basically a wide with 0 or 1s. What about the remaining 1%? Well, the latest senior instruction set, so AVX512, SVE, yeah, most RISC-V also, they have very large registers, up to 1024 bits. So they have up to 64 elements. Okay. So they decided to do something which is not a bad idea. What about storing the mask as bits in a single integer? Because if I have at most 64 value in my register, I can store them in a 64 bits value. So what do I do if I ignore the first one, okay, of my, how much is that? 4, 8, 16 element register, okay, right? Well, everything is at 1 except the first bit. Okay, so you have 1, 1, 1, 1, 1, 0. So that's probably -2. So those computations are done mostly by the compiler because they are involved in constant integrals. So it basically costs us nothing. Okay, we compute -2, we put it into the register, and then we mask as if it was nothing. So we have this flexibility, and if we go back, because I think I did a mistake. I did the mistake. Oh, nope, I didn't do the whole mistake. If you go back to the documentation, to add, yeah, that's what we speak about when we, sorry for the elders. That's what we meant when we have these logical value things, okay? And if we look, oh, wow, we have other things. We have other things. Let's see what we have. We have we have a thing. Yeah. So let's move on operations because there is a lot of things we still have to have a look at. So as I said, we have like a fully vectorized CMAT. We have all the basic things that we want to do on variables like add, sub, bitwise, whatever, basic math like square root and stuff. The special functions, polynomials. We have intra-register reductions. We look at that. Shuffles. And as we see, they are not quite function because normally when you have a function, you don't just slap a square bracket on top of them. Okay. So actually, most of Eve functions are actually callable functions. They are callable objects. So they are actually small objects with a special API. So the parents do the function call, and the brackets can let us add options to the semantic of the function. And the question is, why do we want to do this? Well, obviously, it's a cool API to have for masking operations, so we can see what we do on the mask. Okay, it's better than having if-else everywhere. But it has another important benefit. If you look at some way of computing some function in simple mode, okay, some of them have a bunch of trade-off. And you can have a look, for example, at square root. Square root, where are you? Okay, I have to. Yeah, square root, PD, that's or PS mostly. Yeah. So we have those square roots, but they are not the only square root we have. We have some reciprocal square roots. We have the square root 14, okay, or whatever that means, actually. And same for the actual square root things. And the thing is that the square root 14 is basically, as the name implies, I'm joking, it doesn't imply anything, but basically it means that you have some, we don't even do the whole inverse square root. We stop at some arbitrary precision because it would be too costly. So you have an approximation of the square root. It goes faster, but it's not the correct result. Okay, it's not that far off, but it's not the correct one. And square root of RS30 do the full computation, couple more cycles, worse latency, but you get the exact result. If we were on PowerPC, we even have 3 levels of precision, square root, okay? If you do doubles. And some other functions are like that. You have a very fast one which is barely usable if you are caring about precision. And you have the very precise one, or you have an algorithm to get you the very precise one, but it costs you more. Question, if I give you an API with square root, and you know it's for doing SIMD computation, the question is, which version of square root these guys are computing? Okay? Is it the fast one, but I cannot rely on the precision? Is it the precise one, but I don't give a crap, and I have to myself do the fast one? So what about we just let people choose? So we have this option system so that you can actually decide which trade-off you want to pay for. Are you going to go fast because you don't really care about the 2 at the power of -5 digit on your square root? You don't care about the fact that your exponential send you none as soon as you go up a given level or whatnot? Or are you very, very precision-oriented, but yet you want to be vectorized because even if you only go twice fast, it's a win. So you cannot, as an AP provider, we could not just force you on one mode or the other. So what we do is that basically most of the time, the regular function is the middle ground between all of this. It is relatively fast, and we do the bare minimum in terms of precision, so it's actually usable. But we don't make any promise of anything else unless, it's a trivial operation, and we know we can do it fast and precise all the time. And if you want more for that, you have to ask for it. Do I have the example there? Yeah. So, okay, let's see. Let's go for the big screen people. So here it is. So we have a bunch of vector. We fill up with some lambdas. Okay. What about I actually? Let's run those. So we fill them up with some values, whatnot. And we do some computation on them. Okay, so we have what we just spoke about, the comparison that do a mask. Okay, the ignore first, okay, in these brackets. But you can have all the things. Okay. Let's have a look at cos there. Cosinus is, well, if you don't know it, sorry to be a bearer of bad news, but there is no MM256 cos PS anywhere. So you have to compute it by n. Okay. So that's already, it's not a complicated function. So just a cosinus, but it's already the place where, well, you have to do it manually, okay, which is not what you want to do. So let's ask something, maybe online also. Again, let's go back to the Lego Star Wars metaphor. You have the basic operations, are fast, plus, minus, multiplication, with another register or with a scalar, and I'm asking you to do an implementation of cos. And it has to be fast. What would you do? What kind of scheme can you come up with to say, I have basic operation on floating points, I need a cosinus? It's also a question for you behind the screen if you want. I don't know if someone will answer on the Discord, but maybe. Let's see. Well, what will you do? Anyone in the room? No? You have plus minus times divisions, constants, and you want to do a cos. Okay, so int, you know how to do this because normally you all did high school at some point. Or maybe you did first year university math courses or something like that. Yeah, well, I mean, we can do a polynomial approximation. Okay, fine. Fine, air quotes. Now the bad question is, yeah, okay, which one? Which one of the, I don't know how many polynomial approximation schemes that exist? Well, you can pick actually any one you want because there will all be sum of products with constants. That's not a big deal. But the big deal is how many polynomial coefficient do you need to get your cosinus right enough so it's usable without having to requiring, I don't know how many operations. Because you can do a Taylor decomposition, for example. It's some kind of polynomial operation, but you need far too many coefficients to get to the proper level of precision. So you can have a look at others, okay? And if you dig enough, you will find some that make sense. And you can actually find some that make so much sense that they are very useful. Because there is another problem with cosine. There is a great difference between computing cosinus of 0.76 or something between 0 and 2 pi if you want, and computing random cosinus of 3069, okay? Because it's not meant to that, but you can say, oh, I mean, cosine of whatever big number is basically cosinus of this big number modulo 2 pi. Okay, and if I don't know if there is many people either there or on things, modulo 2 pi is not the simple operation you think it is. Okay. It is completely not, right? We have the chance that it is reusable, but it's a mess. It's a huge mess. But if you know that your value are already on the what's the name of that? On the circle, the trigonometric circle, or some part of it, you can get rid of that. And when you do computation like this, normally, if everything goes right, you know what's going on. You are supposed to know what's going on. In the sense that you know your data, or you can make your data be of some sort, and so you know if you have to resort to using the big cosinus or something more precise. Okay. And there is actually 4 cases. 4 cases to consider. Okay, the regular one that do everything, okay, which is very slow. The full circle one that makes the assumption that your data are basically between 0 and 2 pi. And what if they are outside that? Well, you get none, because what do you want to get? And then you have the semicircle, which is between, how much is that? It's not centered on 0, so it's like, no, 0 pi, no, that's it. And you have the quarter circle, which is minus p over 4, p over 4. And every one of them is like 2 to 3 coefficients less than the preceding. So you want to have a choice in that. Maybe you don't care because your cosinus is done at the end, it's not a critical part or whatnot, so you can just do cos. But if you need to do something precise in the middle of a very tight loop, maybe you don't want to spend, I don't know how many cycles doing precision computation for nothing. Because you are okay with a non-precise cos, because after that you do some other computation anyway. Or you know that your data are exactly there and you don't want to pay extra for it. Okay. So we have options like that. There is another one which is there on the square root, which is rho. Rho basically means that you want the bare minimum things of the computation. It basically means most of the time that if there is one single intrinsic algorithm to do it, even if it's very bad in terms of precision or whatnot, you are going to have that. No more. We won't even check for, out of range input value or whatnot. I mean, if you pass a wrong value, you will get a wrong value outside. That's not our issue. You are basically in grown-up mode. Okay. And there is the other side of the other side of the mirror, which is a pedantic mode. In this case, we purposefully add checks or correction of precision in that. For example, if you call logarithm or exponential using Eve, you can ask for the pedantic version that will do extra careful computation for very high value of exponential or very small value of logarithm. Okay, and we force the result to be always meaningful. So if you take a very large exponential, instead of having nans, you will get inf, which is make more sense, okay, and so on and so forth. But it comes at the cost of additional tests or additional, step in computation. But you are in charge about what it does. So let's have a look at this cosinus thing. What do we mean by it's doing less work? So let's do the float one, because the double one is larger anyway. So let's do it the dramatic way. Okay, let's start with the regular one. And meanwhile, it's compiling. Yeah, I mean, it's a very important thing. When you try to write in code, you have to care about that. I mean, do I care about precision? Do I care about speed? What is my trade-off limit? Okay, so there is an internal joke between us, which is we should have, we should support the row option on trigonometric function. And the joke is that cos of rho obviously returns 1, because it's correct most of the time. So this is cos, okay? I won't even scroll. You can look at the birth view. Okay, cos probably ends over there. Right? Yeah, it's a big function. So it's a really big function, contains the modulo 2 pi things, and then a complicated, polynomials. What if I know that I am on the circle, trigonometric circle already? Okay, so we were where? There. Let's compile a bit. Yeah, cos stops there now. And if we look at what we do, yeah, we have a bunch of broadcasts, so we are turning some coefficient into y. We have some, you see, we have some ends and compare there, which is basically comparing if we are on the circle for later use. And then we have mulad, so we are doing some kind of, what's the name for that? Polynomials. We have a round at some point because we need to know where we are on the circle. And at the end, we have a blend with the result we computed and nans if we are outside of it. And that's basically this twice because we need to do it on 2 small parts. Yeah, okay, that's better actually. But it's still a bunch of things. Here's a bunch going on. I mean, if we know that we are on the quarter circle, half circle first. Okay, so we are on the top half of the hemisphere. Yeah, we are done about there. And we have less, you see, we have far less coefficient needed there, okay? And if I do the quarter circle, so minus p over 4, Oh, wait, where are we? Yeah, we are done. We have like this. So let's put FMA into the mix, because it's all FMA. I mean, it's a product and a sum and a product and a sum. Yeah, how many FMA is that? 1, 2, 3, 4. So it's a degree 5, I would say. So yeah, I mean, it's very compact. Okay, and we have the correct precision compared to whatever the standard does. Okay, as long as you are in this, slice of the circle. Okay, if you have anything else, you got none. That's it. So we have a bunch of things like this. Okay, so we have the specific trigonometric option, we have the row option, we have the pedantic option. For comparison, we are also having the numeric option. Numeric basically means that you don't care about nouns. So basically, if you compare two whites and there is one where it's nouns, you just keep this comparison. You say, yeah, it's true, and I don't care. Okay. So you can filter out things like this. And again, I mean, back to this funny, oral tradition things. Between 2000 and 2012, there was something like 3 or 4 frog leap into how should we do trigonometrics in SIMD by different people of different comings and going. Okay, we are still not sure that's the best way to do it. There were people doing strange operation on polynomials for trigonometrics that let you basically get the sine and the cosine at the same time, depending on how you do the last operation or whatnot. So there is a lot of things going on. And that's something you cannot, well, you don't want to have to know about that, because what you want to do is computing a cosinus. Because I have a cosinus in my formula or whatever other complex function. Okay. So that's exactly what we try to provide. Okay. We shield you from having to know that there is, polynomials with funky names from the 19th century in a dark book that do exactly what you want. We try as much as we can, however, for those that do like those kind of things. Let's do maybe cross-edge is interesting, or CSC is probably interesting. Maybe this one. Yeah, so we got reference, but this one is not interesting. Maybe cross. Yeah, we got some reference. Sometimes you have the actual paper of whatever implementation we use and what. So we try to give the pointers if you like to know what's going on. For the more mathematically inclined in the audience, most of the complex function we try to evaluate as the polynomials. We usually go with Remes polynomials because that's the best one we have. Some of those functions has very specific polynomials that someone somewhere found out in a cave or something, and the guy just put that on the internet and disappeared. Okay, so we gather those information. Okay, yeah. So, but as I said, it's an ever-evolving process. So maybe we miss something. Maybe we forgot about. Not we forgot about. We don't know about some optimization that should be going on. But most of the time, what we try to do is to try to work around these things by providing proper, how to say that, abstraction on top of whatever this mess. Okay. So now, let's go back to this slide. Two other important things: reductions or intra-register reductions and shuffling. Those are very specific SIMD items, okay, because it doesn't make sense in scalar. And sometimes your problem doesn't look like it's vectorizable until you see that, oh, if I put stuff into a register like that, I can do those kind of operations. Reduction are probably the most obvious, because as what they say, okay, I mean, you are doing some reduction operation, but at the register level. So let's clean up the things a bit. Yeah? Let's have X. Let's see what we can do with that. Let's keep the f function so we can both have the results and the how to say that, the code. So reduction, apply a function across the value in the lanes of a single register. So you have a register, and maybe you need the sum of its lanes. You need to know if all lanes have some properties, and so on and so forth. So we have two kinds of reduction: queries and numerical reductions. Queries are relatively obvious to understand. I mean, is all of x greater than 0? Stuff like that. You can write things like this. And this returns you a Boolean compared to all the other comparison operators that return you a logical. And if we look at what's going on there, let's slash up the execution. Yeah, we do something like this. So the main trick there is that reduction requires you to, a bit like in OpenMP or other parallel systems, you have to do some logarithmic computation over the values. But good news, every register size is a power of 2, so it's rather trivial to do. That's the main idea. Except in some cases, and that's usually true with the queries, for example, you don't even have to do that because you can trick the compiler to do the thing for you. And for example, just you have a test of that. If you want to know if everything in the mask verifies some condition, so you compute the condition, and you end up, as we said, with a mask of 0 and all of 1s. And turns out there is a function somewhere in most of those instruction sets that say, oh, can you give me an integer, which is basically the collation of all the highest bit set of your vector? So how do I know if all of my value verifies something? I do the computation, gather the bits, and it better be whatever integer it is. I mean, so if we have, how much is that? 8 floating points, my value should be 255. So I don't even have to do anything else. Now, if we go down to some other stuff, let's say that what we want to do is do the sum of all of that. So we want to reduce x with add, I guess. Yeah. Okay. So now the code is a bit different. We see that we have 2 adds, then a very nice function, vmushed. Okay. Oh, spoiler! If you are into role-playing games, okay, and you need, exotic location name generator, you can take an arbitrary computation, turn it into Cindy, and just read the intrinsics names. And usually it's exactly what you want. So vmushed, which is probably in the south of Neverwinter or something like that. What is that? It's a shuffle operation. We are going to speak about them. Basically, it moves internals of the vectors. So shushed up basically does the following thing. It slices your vector into 2. Okay, takes the I part, so the 2 first elements, and duplicate it so it fills everything. So you have A, B, C, D, and you end up with A, B, A, B. Okay, and mulch, the other one, slightly north of the first one, do the same but by quarters. Okay, so basically you do a sum, duplicate the 2 first, you do a sum again with that, and then you get a quarter of that, and you do the sum, and you end up with the sum in the last element. That's why the last operation is actually a scalar addition. Okay. And so we can do that actually on a lot of things. So let's see what happens if I do that on larger, operation registers. Sorry. Yeah, we have more of that. Okay, shove. And on double, we should have like 1 stuff. Yeah. We add, we take the part, and we add again, and we are done. Okay. If we go on to better architectures, and we are going to speak about that as a conclusion of here. Oh, no, it doesn't have it. Yeah, so Skylab doesn't have it. There is some architectures where you basically have something that, oh, yeah, you want the sum. Here is the intrinsic that do the sum. Okay. But most of the time, you end up with this butterfly recursion steps. Okay. We have an option on reduction. So instead of having the reduction value as a scalar, you have it as a wide, where the reduction result is splatted everywhere. So that's for people doing, for example, linear algebra. You want to have your values at the end in the register, so you can continue computing in the vectorized. Reduce is actually funny because you can pass it any kind of function to reduce. It knows about the basic one. So, for example, we can do mul. Okay. That's another benefit of having our function being object function. We can just pass them to other functions. But I mean, you can do funny things like you can pass a lambda if you want. So let's do something that makes no sense. Yeah, that's not a reduction, but you see what I mean. I mean, let's just do whatever. The result won't be great, but yeah, we end up with having the correct cascade of whatever, or even look at it. He saw the FMA all by itself, so even better. So you can pass an arbitrary reduction function, but if you pass one of ours, we know about it and we do the optimized version. We always saw another reduction when we first did the Sterlen. We have first room. Obviously, if we have first true, you guess we have last true, okay? And we have count true, which counts how many true you have in a logical, okay? So this one is a bit more of a doozy because we need to do some fix up, but that's because AVX512 is a piece of crap sometimes. Let's have a look at the AVX2 one. Yeah, so the computation go right, and then we have these small things because we return an optional. Okay. And if we do control, which is actually a better one, what do we do? Well, we do the comparison and we just get the mask and we do some n to keep up the value to whatever it should be, okay? And we do a pop down, which is exactly what we do. The number of bits equal to 1 is the number of true in our mask. So we all have that. And one of the applications of those queries and reduction is, for example, you can vectorize algorithm with a while in it. Because what you are going to do is that you are going to do your vectorized condition in the while, and you are checking that while any of these are false, you want to keep doing the loop. But in the loop, you compute everything. But you don't want to go further for those that are already there. So you are going to do mask operation with the computation of the mask you already did. Okay? And so you can actually vectorize stuff like, okay, you have something with a while and so on, which is something else that some auto-vectorizers have issues with. So now, to finish the first part, let's see those shuffle in action, because we saw some generated by our function, but we can actually do something with it. So let's go back to AVX2, let's execute the code, all right? And what if I loaded something in my registers, and for some reason I need to reverse it, okay? I need to swap the values. Let's have a look. This one is a bit more complicated because it's not that we want to do some computation. We want to take the values of the things and move them around. So for some basic operation, like you want to duplicate, you want to reverse, you want to broadcast, we actually have a function. So you can call reverse. Okay? And reverse will probably reverse, okay, normally. And so, yeah, we end up having those special intrinsics. So, yeah, we reverse the thing. Fine, okay. But sometimes it's more complicated than that. Maybe you have one register and you need to do some arbitrary movement inside it. One reason you may want to do that is because your scalar code was actually written with a non-trivial memory access pattern in the. And we are going to see that after the break because it will introduce us to the stencil computation. When you have a non-trivial memory access pattern, it's sometimes feeling like you cannot vectorize that. Except you can by loading the things regularly, like the Cindy God intended, and then move the value around so that they end up in the shape you want. Classical thing for that is that you have a compressed storage for what's the name of that? For sparse matrices, and you need to do some operation on it. The good way to vectorize that is basically you are going to read your compressed version of the matrices, and you will unpack it into small matrices with 0 where they need it. You do the operation, and you compress back. So now, let's say we want to shuffle X with a non-trivial thing. So we have a shuffle function, takes a register or two, depending on what you want to do, and you can pass it a pattern of permutation. You can pass it a pattern directly, like you know that what you want is, so it's AVX2. So you want, for example, 0, 1, 7, 8, 2, 3, 5, 6, and I forgot 1, 4. You want to shovel it like this. So the pattern index you pass there, why are you not happy with that? Yeah, because the 8 has nothing to do there, okay, obviously. So, and when you know what you're doing, so the 6 is probably there. Okay, now it makes sense. Because I was like, where's the 4? So let's simplify the generator there because it's a bit complicated. Let's just say it's 1 plus I. It will be easier to see what's going on. So we have 1, 2, 3, 4, 5, 6, 7, 8, and we end up with 1, 2, 7, 8, 3, 4, 5, 6, which is exactly what we asked it for. What happens? If you look at the things over there, it's basically the same function as before. Above a given level of CMD supports, you mostly have a permutation intrinsics in your instruction set. So you need SSE4 for x86. PowerPC have one right from the start. ARM has one right from the start. And so usually what we do at compile time is that we are examining this pattern, okay, and we try to see if it's actually something we know to do better than just shuffling around. Okay? So let's see if I can make one without looking stupid. Which one is it? 4, 5, 6, 7, 0, 1, 2, 3. So basically, I take half of the things and I put them this way. Yeah, okay. And obviously, I have a permute there. Okay, I need to go down to SSE 4.2 maybe. Oh, okay. Yeah, except I have less things if I am there. Okay, so let's do that. So you see the problem is pattern, by the way, that if you change your architectures, you need to change it. And we don't like that. Okay. That was unintended, but it's a good thing. Okay. Oh yeah, it's still a pitch of V. Okay, well, okay, we could look at, but sometimes we generate something else. Some compiler doesn't like what we are doing because they think they are smarter than us. Sometimes they are. No, this time, okay. So sometimes they look that we are doing some permute, and we don't know there was something we could do better, and they do it better for us, so that's cool. Yeah, you see that if I wrote a pattern, I have to know exactly how many things I have to have inside, okay? And so if you change your targets, you may need to change the pattern, and you don't want to do that. So another way to do this is to call as pattern, and as pattern actually takes, I will let you guess, a lambda function, obviously. Takes the index, takes the cardinal, because sometimes you need to have the size. Well, let's write reverse. Reverse is basically, what is that? That, something like this, if I'm not mistaken. Cardinal minus 1 plus the index, or not? Oh, yeah. What about giving a name to the variable? Yeah, it is. So right one. Yeah, so that's reverse. Okay. Well, it generates the correct code anyway because we don't have any intrinsics there. But yeah, it's compiled thing. So this is actually a lambda function. It's not very clear that, but basically it's used as a constable lambda function. So everything is computed at compile time. So there is no runtime things going on there. If you need to have a runtime shuffle, okay, you have a function called lookup, okay, that can do that. Okay, so we can do some computation. We can mix match, data when they are there. That sounds cool because maybe we can start having a look at how can I do some more complex computation. So two things we are going to have a look at. First, that's fine. I'm doing computation on a single vector, but what about, maybe I have like arrays of data. So how do I go from that to actually computing over data? And what kind of shenanigans can I do when I have non-trivial memory access pattern? So I think that's the break. It is. So see you in how many time? Half an hour? Okay.